All right, so hello class, welcome back. So this is lecture 6, and today we're going to, in a brief, somewhat brief, set of slides, attempt to extend the results from the previous lecture, lecture 5, on controllability to the topic of observability. So, before we had controllability, and now we're at observability. So again, observability is a property of the system map, or the property of this box here that we write down, from our inputs to our outputs. And controllability told us something about this system. Specifically, it told us what the effect of this input was on the state, right? So how we defined a solution, explicit solution from the input to the state. And in this sort of dual aspect, and we're going to be talking about a lot about duality in this lecture, we're going to sort of complete that picture by then talking about what the effect of this state here is on the output, y of t. Remember, these are functions. Okay. So specifically, observability is defined as, we'll define it formally in the next slide, but what kind of outputs are produced by these states. And so we're going to cross off here the input, the effective input, and we're going to try and isolate the effect of the initial condition, x naught, as it maps to the state and then hence to the output. And then we'll talk, so that's our system property. And again, we'll try and relate that to the system description, which is right, x dot equals ax. This time, of course, we have no input, and our output, which is cx. Right. So this our system description is these two matrices. We parameterize our system by those two matrices, so we have properties of those matrices, and we'll try and relate them to a positive matrix, again a Lyapunov function, which we're going to call the observability Grammian. And of course, once we have things in terms of a positive matrix, that allows us to then express these as LMIs, these system properties as LMIs. So again, not focusing on, try and avoid focusing on properties of these matrices, which are just one particular representation of the system, but moving to Lyapunov functions which encapsulate those properties more explicitly, and then LMIs is a search for those Lyapunov functions. Right, so definitions, right? So again, we get rid of the input, no BU of t, right? Cross that out, no BU of t there. We do allow for a non-zero initial condition in this case, because remember, we are this is sort of an intermediate sort of property. Before we had u to x, and here we're going to start on the effect of x as it maps to y. Right. So for an initial condition, again, we can find an explicit solution for this system, y of t equals c e to the a t x naught, right? We know what that is. And so we're going to be focusing on properties of that map here from initial condition to the output function. Now the initial condition is a function on Rn, so a vector, and the output, right, is a function, right? So we usually write that as L2 for a Lebesgue integrable function. So we're not going to talk about L2 quite yet, but we're getting there. So basically, the observability property of that map, of that system, right, is, well, we say that a system is observable, and now we qualify that definition on a fixed interval, although it doesn't matter what that fixed interval is, as we'll find out, as it wasn't an issue for controllability. Again, if it was controllable on some interval, it's controllable on every interval because it's a linear system. Right? But we define it to begin with on a finite interval. And so the idea is, given observations on that finite interval, right? So for a given initial condition, given observations on that interval, can we reconstruct what the state was that created those that output? Right? So can we map based on those observations, can we figure out what that initial condition was? Right. So if that initial condition, for example, has no effect on the output, right, that state will not be observable. Right. That makes sort of intuitive sense. Right. So armed with that definition, right, we can sort of move to our next definition, which is that map, right, the solution that we talked about. And we call this actually the flow map. Sometimes we refer to this as the solution map, but there is the solution map is not usually defined in this way because that would be like a map from initial condition to state. That's how it's usually defined as the solution map. So we'll keep our terminology of flow map in there. Right, so the flow map, right, that's what we're going to call it, is the output produced for a given initial state. And then we have output. Now we have this funky sort of weird notation here. Don't get too alarmed about this. Remember, this is a vector of length p. And the output here is a function, it's y of t basically, this is y of t, which maps time, that's t is r for just scalars, to an output. And here actually I've defined the output as the same size as the state, so that's a little bit funky as well. This should really be something else like m or something like that, or q. Q is more common, I think. Right, so that maybe this is n and this is p, or something like that. Anyway, so there are different dimensions. This is the dimension of the output, right, and this is the dimension of the state. Okay. So that's just a convenient bookkeeping way. This psi sub t of saying the initial condition gets mapped to this output y of t. So it's mostly just bookkeeping, so don't get too alarmed about it. Right, so that's what it means. So then, given this definition, right, this sort of bookkeeping notation, we can sort of more conveniently represent this definition here of observability, where we say the pair CA. And here I've sort of like alternated my my order of matrices, but don't get too confused on that. This is the more common one. We should really make that CA. And anyway, so we can say that this is observable if and only if the kernel and of this map is 0. So that basically that no state or no initial condition gets mapped to a 0 output, right? So y of t equals 0 for all t, and that's my little for all symbol there. Right? So y of t is 0 for all time. That implies that the initial condition was also 0. Right. So that's what that means. This kernel definition we have right here. Right. So another corollary, right, of that, another way of thinking about that is the invertibility of this map, right? So given the output, we can figure out what was the initial condition. And those two concepts are equivalent, it turns out. Yeah. So again, that's what I just said on the previous slide. So again, we're going to, there's a lot of similarity to what we covered for controllability. So in particular, we can define an observability matrix. Remember what the controllability matrix was. That was C of A, B, and that's, I wrote them in backwards order, right? C, here it's CA and here it's AB. So the controllability matrix, if you remember, was B, BA, all the way out to BA n minus 1. Right, so that was the controllability matrix. This is similar. Oh, sorry, I got these backwards. On the other side. So this is similar to the observability matrix. Here we have maybe a skinny matrix, as in it's like a tall matrix. And here this is a fat matrix, or a wide matrix if you prefer. Where C here gets put in front of everything, right? So, and then we have a state. And so you can think of this again similar to how you thought about the controllability matrix. If a state shows up directly in the output, right, then that's the first entry. If it gets mixed with some other states through the A matrix and then shows up in the output, that's the second entry, all the way down mix, and n minus 1 mixes. And that's the last entry, or last row, it shows up in there. So remember that C is generally a wide matrix, right? So it's generally thin. So when you stack these things up together, it's not too tall, because, right, you generally have fewer outputs than you have states. Right? This is your C matrix. So again, right, it's not quite as tall as it appears right here. So that's the observability matrix, and you can see it has very similar properties to the controllability matrix. If you sort of transpose this thing, then you get basically C transpose A transpose C transpose, something that looks very similar to the controllability matrix, right? Something like that. So there's a lot of similarities here, right? And of course, we can use those similarities, right? Because we studied the controllability matrix in some depth already, although we didn't go through the proofs of it in any way. But we can use those proofs, if we had gone through them, to establish these properties of observability based on the observability matrix. Right. So we say this is theorem 4, right? So it's a big result. But it's sort of stated without any pretense here, which basically says that if the system is observable, right, that is the kernel of this map is 0, that's equivalent to the kernel of this matrix being 0. So it means basically you only have to mix your state n minus 1 times before you're assured that if it's going to produce an output, it has produced an output, right? And that's the Kaylee-Hamilton theorem again. I have this intermediate step here, which is saying that the kernel of this matrix, right, is just the intersection of the kernel of all of these little subspaces of these little matrices here. So if a state gets is unobservable in this row, and this row, and this row, and this row, then it's not observable for any of the rows. If we just put a CX there. And that's equivalent, it turns out, to observability, right? That this kernel is 0. And that's stated here formally in what is equivalent to the sort of very powerful result we had last time. Well, actually, sorry, that's not the. I'm boxing the wrong thing here. This result, which is equivalent to the very powerful result we have for controllability. Right. Before I give that result, though, I should define the equivalent of the controllable subspace, which in this case is the unobservable subspace. Right? So the unobservable subspace is a set of states which never get mapped to an output. Right? So they never appear in the output. So it's the X such that we can say O C A X equals 0, right? Put a little set notation there. So this is, by the way, set notation, right? So this is how you always write sets, right? You say X is in some field, in this case Rn, and then you put some constraints on the elements of those sets. And so in this is the kernel of this matrix O. And of course, what we've stated is that is equal to the kernel of this flow map. So this is a subspace, obviously, similar to how because right, this is a matrix, and so the kernel of a matrix is a subspace, and so obviously these kernels are also subspaces. And so we have a particular name for this subspace, which is the kernel of this matrix, which is N sub CA. Remember, for controllability, we had C A B, which is a set of states we could, similar, we could drive to 0, or reachability we could get to, right? So they're the same concepts. Well, actually, it was stabilizability for the ones we could drive to 0, but the controllable subspaces is the one we could reach. So now we have this very powerful theorem here, which says that the kernel of this operator is 0 if and only if the kernel of this matrix is 0. And so that's like already sort of encapsulated in this definition, but we sort of prematurely stated it perhaps. And then, of course, the big next step is saying that the system is observable. Right. So that those both mean observable. If and only if the observability Grammian is full rank, right? So it's a matrix, it's a symmetric matrix Y here. This is the observability Grammian. If and only if that's a full rank matrix, right? So if we look at this Grammian, it's defined here. Right? So I'll highlight that one because it's an important matrix. So that's the observability Grammian. So if we look at that, let's change color here for a second, just for fun. We'll go to, try this one. Okay. So if we look at that observability Grammian, right, and we think about it as a matrix, a positive matrix, X naught transpose Y X naught, right? If we look at what that is, right, it's integral of X naught transpose E to the A transpose S, C transpose C E to the A S X naught ds. And remember what this is, right? That's psi, well, I should say psi f sub s, right? X naught, or I can write the subscript over here of s, if we like. And of course, that's equal to the output produced by that initial condition. So x x naught transpose y x naught, right, is just the square integral of the norm of the output produced by that initial condition. So obviously, right, if this is 0 for any initial condition, or if the kernel here, if it's not full rank, if it has something which you multiply by and it's 0, right, then there's an initial condition which produces no output. Right? So that's a very useful concept, and we'll sort of extend it again in the next slide to that Grammian, take that Grammian and extend that to the observability ellipsoid the same way we did for the controllability ellipsoid. So again, right, here what we've done is we've taken the properties of the solution map, which is psi t x naught, the output produced by that, and we've that's property of the system. We've related it to some property, the particular kernel, the rank of this matrix, rank of the matrix. And then we've related it to the existence of a Lyapunov function, which is the observability Grammian. And then, of course, what we're going to do, right, is the existence of a positive matrix allows us to pose the problem as an LMI. The observability Grammian, however, remember this is how it's defined, and we can just write that. Well, okay, because we don't have the x naughts right here, so we'll leave that alone. So we can just write down x naught transpose y x naught is the square integral of the output produced by that initial condition, and here the square integral. That's the L2 norm, so that's what that little notation means, right? So this so not only says that something about whether the system is observable or not in terms of rank of this matrix, right? Rank equals n if and only if observable. And again, this is notation of if and only if. So that means they're equivalent. It tells us something a little bit more quantitative, a little bit more useful in terms of how observable these states are. So it tells something very quantitative. And then, again, as with the controllability, there are a couple ways of interpreting this matrix. As I argued here, right, as I pointed out in this little blurb here, right, there's in some ways the interpretation of the observability Grammian is a little bit more direct than the interpretation of the controllability Grammian. And so the ellipsoid, you would think, right, would have a sort of a similar, more direct interpretation than the controllability one. But actually, the observability Grammian, the observability ellipsoid, and this is what that is, this gray area, is a little bit harder to interpret. So first of all, remember the Grammian or the ellipsoid for the controllability case was defined a little bit differently. So specifically, that was x such that x transpose W inverse, and here that was the controllability Grammian. X transpose x inverse is less than 1. And here we don't have that inverse. Right. So constructing our ellipsoid is actually is a little bit different. For the controllability ellipsoid, right, the lengths here were That's what this space is. So if you want to find the lengths in various directions, right, you do an eigenvalue decomposition. That's what these are, the eigenvalues. And these directions are the eigenvectors associated with a particular eigenvalue. Right, this is x2, and this is x1. Right, so the directions, right, the interpretation of the directions are the same, but the length that you go in those directions is a little bit different because we didn't invert the matrix first. And so the length in these directions is 1 over the eigenvalue, right, as opposed to here where these lengths were just the length of the eigenvalue. Oops. Right. So again, right, the interpretation is fairly straightforward. This envelope tells you, what does it tell you? It tells you that these are the sets of points, well, the edge of the envelope at least, is a set of points which produce an output of size 1. So it tells you quantitatively which initial conditions, specifically given by these eigenvectors, will produce what size outputs. So in particular, if you take this initial condition, right, that produces an output of size 1. If you take this initial condition, that'll also produce an output of size 1. So then how do we interpret this, right? So if we were in class and this was interactive, I would ask you, which of these 2 points is more observable? This one or this one? Well, I mean, just based on your sort of like size interpretation, if you weren't thinking very carefully, you would say, well, this is bigger in this direction, so obviously this one is more observable. But that's actually the exact wrong way to do it. That's the interpretation for the controllability ellipsoid, right? But for the observability ellipsoid, the idea is the opposite. So you need to go this far in this direction, right? You need to go this far in this direction in order to produce an output of size 1. Whereas in this direction, you only need to go this far in order to produce an output of size 1. So this one is more, this state right here is actually more observable. Because you don't have to go as far, or you don't need as big an initial condition in order to produce an output of size 1. Right? And so this is less observable, obviously. And then you can take this to the extreme, right? If this length here is 0, then this direction. So if this length is infinite, then the direction is not observable at all. Right? So you'd have to go infinitely far in this direction in order to produce an output. Right? So the shape of this ellipsoid is an ellipsoid, so the controllability and observability cases are the same in that respect, but the interpretation is really quite opposite. So the big axes are the ones which are weakly observable, unlike in the controllability case. So in many ways, again, right, the controllability case and the observability case are opposites. That's the concept of duality, but they're not true opposites, right? So I don't want to take the idea that they're opposites. In truth, they're adjoints, right? And what do we mean by adjoints? Well, we haven't defined inner products and all that stuff, so we won't get into that too much. Right? Again, this is what we talked about before. So Theorem 6, right, gives conditions under which the kernel is 0, as opposed to the sort of opposite in the case of controllability, where we're giving conditions under which the image is full rank, right? Which is sort of the opposite of 0. And these are related, right? Because these notions of image and kernel are dual as well. So if we have a matrix M, well, what is the image of that matrix? Well, it's a set of Y, right, equal to mx. So there exists an x such that you can get to Y, right? So this is well, if M is a square matrix, then we can say that the image of M is Rn if and only if, and there's that if and only if symbol, the kernel of M is empty, right? There's nothing which produces 0, right? So there's this result in that case. You can also interpret it, right? So the images of M is all of Rn, right? If and only if the perp space of M transpose, so the perp space of we'll talk about perp spaces a little bit more detail later, but the set of vectors which is orthogonal to M transpose, the kernel of M transpose is 0. So, right, so that basically there's no left kernel, I guess you could say. So that means that there's no Y such that Y transpose M equals 0. And I should say empty set. Actually, I shouldn't say empty set, I should say 0, right? Because 0 obviously produces 0. So, okay, but that's cheating. Right? So there's this relationship, right, between image, right, and kernel, right, so that the image is the perp space of the kernel of the transpose, and so the image is full if and only if the kernel is empty for square matrices. All right, so that gives us an introduction to Grammians and ellipsoids. In the next slide, we take that duality and formalize it a little bit, just what I was taking notes on the previous slide. Right, so we extend that duality a little bit further, right? So by showing that we can analyze controllability of a system by looking at observability of the dual of that system, so to speak. Right. So specifically, we rely on this fact here, right, of the relationship between the observability matrix and the controllability matrix, or the transpose of the controllability matrix of sort of this transpose system, right? So if we take this is a dual system where A equals A transpose and B equals C transpose, and we construct the controllability matrix for that, and then we transpose it, we get the observability matrix. And likewise, right, if we take the observability matrix, right, and we set A equals A transpose, and we set C equals B transpose, and we construct the observability matrix, then we get the controllability matrix of the original system. And so we leverage those relationships using what we were talking about on the previous slide to show that controllability, the controllable subspace, or controllability and observability and the controllable subspace and the observable subspace are really two sides of the same coin. So remember this unobservable subspace is the kernel, the set of vectors which could map to 0 of the observability matrix. And using that relationship I gave on the previous slide, well, the kernel of a matrix, right, is equal to the perp space of the image of the transpose of that matrix. So that this here is OCA transpose. Right? So the kernel of a matrix is equal to the image of the transpose of that matrix perped. So the set of vectors which are orthogonal to that. And so we get that the unobservable subspace, right, is equal to the perp of the controllable subspace of the dual system. So the perp of the controllable subspace. And likewise, the controllable subspace, remember, was the image of the controllability matrix. And the image of the controllability of any matrix is the perp of the kernel of the transpose of that matrix. So this is C of A, B, actually C of A, B transpose. In that transposed matrix by these relationships here gets mapped to the observability matrix of the dual system, and so this space right here, the kernel of that observability matrix, is the unobservable subspace of the dual system. So that's also the dual system here, but the dual of the primal. We have a different primal system. So we can use these relationships to straightforwardly show, right, that a system is, say, observable if and only if its dual is controllable. And likewise, a system is controllable if and only if its dual is observable. Did I say observable? And where for the input, right, system AB, its dual is A transpose. Well, we usually list them in opposite order. So B transpose, A transpose, and for the output system, we had CA, and its dual is A transpose, C transpose. Right. So we can use that relationship directly to get this the following LMI. So where we just use the test, the LMI we had previously. For controllability. So we test observability by testing controllability of the dual system. Right? So this is the controllability LMI. For the dual system, A transpose, C transpose. Right? And so we don't even need to prove this, right? It follows directly. It's a really corollary, I guess I could say, of the LMI for controllability. Right? And so we just see here. Remember this was the LMI for, well, it's not really an LMI because it's equality constraints, but we'll ignore that for a second. This was the one for controllability, and here we've just A goes to A transpose goes to A. B goes to C transpose, and B transpose goes to C. So it's exactly the same thing. And then nicely, of course, right, that gives you the observability Grammian, right, for the system. So in a sense, we get observability in all of its corollaries for free, all of the LMIs for free, just because we've already studied controllability in so well, and we applied duality. So this is again, right, just some bookkeeping. I formally here defined the perp space because I didn't really formally define it on the previous slide. So the perp space of a set, right, of a set is a set of vectors which are orthogonal to every point in that set, or every vector in that set. Right? So that's the definition, right, of perp. Of perp space. So for a given, actually, it doesn't even need to be a space. It can be a set. But once you define the perp space, that is in fact a subspace. Regardless of what X is. Okay. And then, of course, you can get the perp of the perp, right? Is in certain cases that's equal to X. That you get back the original space, but only if X was a closed subspace to begin with, right? So, so X is a closed. And we haven't defined closed either, but you'll bear with me, I hope. And actually, that's only if. All right, so, okay, and here I've got some other bookkeeping stuff, right? So remember the map to, from U to, this was the map for controllability from U to X, and here we've got the map from X to Y. And in both of these cases, right, the results follow just by plugging in this series expansion of the matrix exponential here, right? And then Kaylee Hamilton says we don't need to go any further than n minus 1. Right? Actually, we can stop at n minus 1. Right? Okay, so that's that very quickly covered sort of the definitions of the observable space, observability Grammians, the interpretation of the observability ellipsoid, all of these very important concepts, all of which, however, through duality, almost follow directly from the controllability analysis. In the next part of this lecture, which again will not be too long, I hope, we will cover something new. Well, duality is new, but we will now cover something completely different. Now for something completely different, right? In the immortal words of Monty Python. We'll talk about observers, which don't really have an equivalent for controllability. So, but I'll stop here for a moment and let us all take a break.